Hey guys, welcome to another episode of MSK Coding, and in this episode, I'll be showing you another program I made. This program is about the Sieve of Eratosthenes. If you don't know what the Sieve of Eratosthenes is, it's pretty simple. It's basically a very ancient way to find like a list of primes up to a certain amount. Basically, how it works is you have a grid or just a list pretty much of all numbers up to the amount given. Then for every for every unmarked number that you come across, you mark it as prime, and all multiples of that number you mark as composite. Then once you keep going through, again, every unmarked number is prime, and then you remove all of the multiples of that number from the list. And so once you've marked every number with either prime or composite, you're done, and you now have a list of all the primes up to that number. So we can start with understanding the code. So here we import math. There's going to be some math involved here. Then we do int equals int of input, or input, not input. Basically just an integer version of the input. Then we have L equals false plus true times int minus 1. What this does is it puts the first value in L as false, and every other value it makes true, and the entire length of L is INP, the input. Then we have a simple for loop. The incrementer is I, that's what gets incremented. And then we have range right here. 2 math seal, math squirt, in 2, pretty easy to understand, just 2, I guess. Then math seal, what this does is it just gets the higher value, and so once it gets excluded from the things that we're going through, because that's how range works, the highest amount gets, or the end amount gets excluded. So we make math seal to make everything before it true, everything before math.squirt being a value that I can get to. And so here we use math.square root. Here we have square root, sqrt. Then we have inp as the argument to math.square root. The reason why we square root it is because it makes it more, more efficient, and so it makes it less operations needed, because we have this whole if statement over here and a while statement, and if we didn't have the square root, it could take much longer. And the reason why the square root even works is because of how factoring works. So 5 times 20 is the same thing as 20 times 5, but if we're just incrementing the first number, you have to go 15 more steps until you get to 20, when you could just be at 5. And so basically all the past the square root, it all becomes redundant. Basically then, line 5, if L of I minus 1, that just checks if the corresponding list value of the I guess, the corresponding list value is true if it hasn't been marked false yet, if it could be still a prime. The reason why we have I minus 1 is because, let's say you had 2 here. 2 minus 1 is 1, and so L of 1 is the second value in L, because indexing starts at 0. Then you have selected being 2 times I, and so what this does is just selects 2 times I, and the reason why it's only 2 times I and not just I is because we have to delete or mark composite all of the multiples of I, but not I itself, because I could be prime. Who knows? And it probably is prime because it passed this if statement over here. Then you have while selected is less than or equal to input to stop it from going forever. You have to have a condition. Then, what happened there? L of selected minus 1 equals false. The reason why we have minus 1, same reason why we have minus 1 over here. It's because indexing starts at 0 instead of 1. But anyways, we set that part of the list to false, saying that it's composite. Do not go to this number again. And then we have selected plus equals I. That just increments the coefficient of I. So instead of 2I, it would become 3I over here. Then once it goes through all of the numbers, or goes to all the numbers asked for, it goes to line 10. And line 10 is, it's the longest line actually here, but it is pretty straightforward if you can break it down easily. So you print the thing inside, so you output it, then you have the asterisk. That is pretty easy to understand once we look at the the list here. List comprehension is the exact term for it. So if we look at each term of the list comprehension, we have x plus 1. The plus 1 is there for pretty much the same reason why we have minus 1. We're taking an index and making it into a value. And we're using an index here, as you can see. So for x value in enumerate, L, and what enumerate does is it returns the index and the value of everything in a list. So maybe over here in the console, if you shift your eyes to the right, you can see how list of enumerate of, let's say, hi MSK coding will return 0, hi, 1 MSK, and 2 coding. So it's index and value side by side. And so x here is the index, and the value is what we check here. In the third term, if value, just as saying if it's true, so like if it is prime, pretty much. And then if that is true, we put x plus 1 into a new list, and again x plus 1 because we're taking the index. So in this case, let's say if you have 2, it would be index 1, but we have to add 1 to make it the number 2, and so 2 is prime. This asterisk here is just to make it space separated, pretty much. So like if you had the list 1, 2, 3, it would be 1 space 2 space 3. So now that I've explained the code to you, it's time to test it out. So we'll do 10 maybe, 2, 3, 5, 7, that's correct. Then 100. It took a bit longer, but we still have all the prime numbers. 1,000. It took a tiny bit even more longer, but we still have all the numbers. 10,000? That's a lot of numbers there. 100,000? Now we're getting into territory that's just like, wow. There are a lot of primes. In fact, there are infinite amount of primes. And that's something that's been proven. So, yeah. Hope you liked this video about primes and the Sieve of Eratosthenes. And I'll see you in the next video. Bye!